And I'll try to organize it in such a way that it will make some sense to you. Of course, is there going to be some heavy lifting outside of the class? Yes, okay, you're going to have to do all the practice problems and everything. But yeah, let's take a look at it. And yeah, just a lot of concepts that we're going to take a look at, but all of it is manageable, okay? Every single thing we do in this class is manageable. So let's start out with where we kicked off last class. So we said there's two main types of reactions we're going to cover in this class: substitution and elimination. In today's class, we're going to focus mainly on SN2 reactions, and then time permitting, we'll get into the E2 reaction. So we've got our substitution reactions, and we have our elimination reactions. We're going to look at alkyl halides a lot. Remember, we call those a substrate sometimes. Instead of just calling it a reactant, we'll call it a substrate. So if you hear me talk about a substrate, I'm usually talking about an alkyl halide of some sort. What else? We said good leaving groups. We had to know what the good leaving groups are, so we reviewed those, and we covered one new leaving group. But before we get into new stuff, I wanted to go through the nomenclature with you. Just as a gentle reminder, whenever we're talking about substitution reactions, the alkyl halide, or the halogen, has to be attached to an sp3 hybridized carbon, okay? You can't do any kind of substitution or elimination on sp2 hybridized carbons, and so don't stress about those during this chapter. Furthermore, last lecture we said, well, the SN2 and the E2 processes, we could draw mechanisms for those. For the substitution, the SN2, we have a nucleophilic attack and a loss of leaving group occurring simultaneously. A mnemonic you can use for this would be SN together. Both steps occur at the same time, right? They happen together, the nucleophilic attack and the loss of leaving group. Then we have the substitution, the elimination, the E2 reaction that is shown here. And you can see there's a total of 3 curved arrows in this reaction mechanism. You see that the base is taking the proton, you're forming a pi bond, and you're losing a leaving group at the same time. Now, sometimes we can have a reagent like a hydroxide, and we talked about this last class. I said a hydroxide ion, and again, there's no trick questions in my class. Is hydroxide a base? Yes, absolutely. It's a strong base, right? Is it also a good nucleophile? The answer is yes. And so if you have an alkyl halide and you have hydroxide, the question that you have to ask yourself is, what mechanism is going to occur here? Will it be substitution or will it be an elimination? And I know you guys are all very astute, and you probably noticed right away that there's a difference between these two alkyl halides, right? If you look at the alpha carbon, remember the alpha carbon is the carbon the halogen is attached to. If you look at this alpha carbon, it has only one carbon attached to it. However, if you look at this alpha carbon, it has 1, 2, 3 carbons attached to it, okay? So we call the first one a primary alkyl halide. The second one is a tertiary alkyl halide, and so that is going to have something to do with whether substitution or elimination is going to happen. Then we said, well, if we have a reagent like a hydroxide, which can function as a nucleophile or a base, we're going to end up with mixtures in a lot of cases. And you and I have to be able to say, well, this is going to be the major product, this is going to be the minor product. And so I'm going to guide you through that over the course of this chapter. We also said, okay, if we look at a molecule, like let's say we have methyl bromide, a pretty simple alkyl halide. You get a methyl group, you get a bromine attached to it, and you would say, well, I can see that this is going to react in a substitution reaction for 2 reasons. Number 1, the bromine is more electronegative than carbon, right? It pulls electron density away from the carbon, rendering the carbon delta positive. And also, you guys know that a bromide is a good leaving group. Why? It's the conjugate base of what? Hydrobromic acid, which is a strong acid. Remember I said that? A good leaving group is the conjugate base of a strong acid. And we see those here. We reviewed this last class. We said, what are the strong acids that we know? And until yesterday morning, you guys all knew these 3, HI, HBr, HCl, right? Those are the classics, okay? Then we have H3O+. We maybe don't think of it as much, but hydronium, H3O+, is technically a strong acid. It has a pK of 0. And then I introduced you to this new strange looking acid here. And I tried to relate it to sulfuric acid. I said, if you look at this molecule, it has a lot in common with sulfuric acid, okay? We call this a sulfonic acid, and the name of this compound is toluene sulfonic acid, or It has a short name, which is tosic acid, which is neither here nor there right now. But we said the conjugate base of this acid, which has a pK of -3, so it is definitely strong, okay? Its conjugate base is called a tosylate, and we're going to see tosylates now as leaving groups many times in this chapter. So let's review. We've got good leaving groups. We've got iodide, bromide, chloride, water, which is the conjugate base of hydronium, and now we have this new one, which is a tosylate. All right, so there you go, a tosylate. Right away, before I even get into the nitty-gritty of tosylates or whatever, okay, if you think about if you could put a tosylate, or if you had a tosylate on an organic compound, do you guys see that it has a chromophore in it? Do you remember chromophore was double, single, right? Had the double and single bonds alternate here, double, single. Do you guys remember what's so great about those compounds is that you can view them under what? Ultraviolet light. Remember when you run a TLC in the lab? Did you ever think about that? All the compounds that you do, they always have some kind of ring in them, right? There's usually conjugation in there because you can't see a straight chain alkane under ultraviolet light. It doesn't absorb UV rays. Okay, so this is another reason why we like things like tosylates. Anyhow, I'll come back to that later on. So where I want to hit, pedal to the metal today is to try to name a few compounds. And we said when we're naming an alkyl halide, we borrow all the same rules that we did for alkanes. The methyl group, the ethyl group, the propyls, the butyls, they haven't changed. They're not going to change, okay? However, if we have a fluorine, we use we call it a fluoro. If we have a chlorine, we call it a chloro, bromo, and iodo for bromine and iodine, respectively. So I went over these rules last class, and then I said besides systematic names being acceptable by IUPAC, we can also use common names. And if you're like, well, how do I know when to use which one? Well, either one is good. I might ask you very specifically on a quiz, give me the common name of this or give me the systematic name of this. However, if you're like, well, when can I use the common name? Whenever you have an alkyl group attached to a halogen, it's an alkyl group that you know, methyl, ethyl, the 2 propyls and the 4 butyls, you can use a common name. Okay? Are there other common alkyl groups? Yes, there are. Okay? But you don't need to memorize. I told you need to know those 8 for this class. So that's kind of what we'll stick to. And one more thing I added to this is if you have a linear alkyl group, like a propyl group that you see here, you could call this compound at the bottom 1-bromopropane because we have carbon 1, 2, 3 in our longest carbon chain. But you can also call it N-propyl bromide. And I said the N stands for normal. So whenever you have a straight chain, you could call it N-butyl, N-propyl, right, N-pentyl, et cetera, so on and so forth, okay? There we go, so a normal alkane. So let's move on, and let's talk about primary, secondary, and tertiary alkyl halides. And we went over the Greek letters, and we said, okay, the carbon that the halogen is attached to is the alpha carbon, right? First letter in the Greek alphabet. We're going to talk a lot about alpha carbons in this class, but I would say we're almost going to talk about beta carbons just as much, okay, because they're very important, especially in E2 reactions that I hope we get to today. So again, just to draw, conclusion here. If you take a look at the carbon that is attached to your halogen, and in each one of these cases it's a chlorine, you look at the number of carbons it is attached to. If it's attached to 1, it's a primary alkyl halide. If it's attached to 2, you see where I'm going, it's secondary. And if it's attached to 3, it's tertiary. Give me a thumbs up if you're with me on that. Yeah, great. Students are usually like, yeah, no problem with that. I can remember primary, secondary, tertiary. Thus, if I was to draw an arrow to this alpha carbon here, no trick questions in this class. Could you tell me, would this be primary, secondary, or tertiary, this alpha carbon? It is? Yeah, absolutely. Secondary, right? It's attached to 2 carbons. Great. Awesome. We're really rocking and rolling with it here. So let's see if we could name a couple of compounds here. Maybe you guys have given these a try already. I gave them a try. Okay, so if we look at the first compound, could anybody tell me how many carbons are in the longest chain of this first compound? Total number of, there's 5, right? There's 5 carbons. Now, Brianna, you came up with that number 5. Should I start numbering where I have this green highlighter or where I have this yellow highlighter? Which one would be more appropriate? Should I start numbering on the green carbon that I have highlighted or the yellow carbon? Yellow. If I start numbering on the yellow one, I have 1, 2. I have my first substituent on carbon 2, but if I start numbering where the green carbon is, I have 1, 2. My first substituent is on carbon number 1. Are you with me on that? Remember, the rule is we seek to give the first substituent the lowest possible number. Don't worry about the rest of them. Just give the first substituent the lowest possible number. Therefore, the green carbon is where we're going to want to start. So I'll just delete this here, and we'll label those carbons 1, 2, 3, 4, 5. Now we've got a 4,4-dibromo, and we have a 1-chloro. Well, what comes first, B or C in the alphabet? The answer is B. Okay, so we're going to list the bromo first. Remember, we ignore prefixes, mono, di, tri, tetra, all that stuff. The only prefixes we don't ignore are iso and cyclo. Ergo, we're going to put this all together, and we're going to say, okay, we've got a 4,4-dibromo. Then we have a 1-chloro. And if there's 5 carbons in this chain, it must be a pentane. Heck yeah. There you go. Pentane. Now, there's no common name we can give to this. There's no common name whatsoever here. We can only give this a systematic name. There we go. All right, what about the next one? Well, this one you probably noticed right away that there's some symmetry in this molecule, isn't there, right? We can draw a line down here. And so whether we start numbering here 1, 2, 3, 4, or if we start numbering here 1, 2, 3, 4, either way we have a 1,4-disubstituted cycloalkane. Are you with me on that? Okay, so we've got a bromo and we've got a methyl. Which one do you think would be more appropriate to put first? Since we can't break a tie with numbers, what would we use? Alphabet, right? So we'd list the bromo first, and therefore I'm going to erase these here, and we're going to say we've got a 1-bromo 4-methyl. We'll scribble that down. We've got a 1-bromo 4-methyl. And what's my parent called here? Cyclohexane, yeah, everybody's favorite. Can't get enough of cyclohexane in this class, right? Okay, the last compound has a chiral center in it. I'm sure while I was yammering on here, somebody figured out, is it R or S, this one? Anybody? Don't be shy. Go ahead. What did you say? Yeah, it's an R compound. Yeah, for sure. Right? The fluorine takes highest priority. The hydrogen is going in the back. I'm not even going to draw it. Right? This group is obviously going to take second highest, and the methyl is going to be third. You're going clockwise. Therefore, this is an R compound. And so when we go to name this compound, we're just going to start with R, and we put it in parentheses and then hyphen something. Now, if I put a yellow highlighter here and maybe a red highlighter over here, which one of those carbons should I start numbering at? Which one would be more appropriate? You notice that either way, you have a substituent at carbon 2, right? But if I go from the yellow carbon, I have 2, 2, right? I have a 2 and a 2 for the 2 methyls, yes? Whereas if I start on the red carbon, I've got a 2 and what would it be, a 5, right? So what's going to be better? Would I want to have 2, so the first way would be 2, 2, 5, and the other way, going the red way, would be 2, 5, 5. Well, this is the tiebreaker, right? A 2 is lower than a 5. Therefore, we should start numbering at the yellow carbon, right? We just keep following the line of succession until we find a rule that's going to break the tie here. So we've got 1, 2, 3, 4, 5, 6. Now we've got dimethyl and a fluoro. Which one of those is going to come first, the dimethyl or the fluoro? The fluoro, right? Because F comes before M in the alphabet. So we've got an R, 5-fluoro. We'll scribble that down, 5-fluoro. Remember, it's FLU. 5-fluoro. 2, 2-dimethyl. Dimethyl, and we've got 6 carbons, so it is a hexane. What do you think of that? Not too bad? Yeah? Go ahead.
Question, when would you use E and Z when naming?
Only when there's a double bond. Yeah, you'd have to have an alkene to use E and Z. Well, look, we'll see some, well, maybe we'll see some E and Z alkenes today, okay?
And then cis and trans, like the first one has 2 bromos in it?
Yeah, so again, cis and trans is either reserved for a double bond or a ring. Yeah, you got to have either a double bond or a ring. All right, so let's move on from there. We talked about insecticides a little bit. Anyhow, you guys can take a look at that. So here's a slide that just blows everybody's mind, right? How many different compounds can we make from an alkyl halide? You know, just to give you like a little story about, you know, something that happened to me, the second job I got in the pharmaceutical industry, which it's hard for me to admit this because it wasn't my first rodeo. You know, I'd been a chemist for a long time, but I was nervous. You know, you're the new guy. You know, you're always a little bit shy when you're the new guy. And they said, they had a target in mind or some kind of starting material, and they said, what can we do with this? What kind of compounds could we make? They said, we'll have a meeting in the cafeteria, we'll just get together, a couple of guys, and talk about what we got. And anyhow, they said, what do you got? And I said, I don't know, we could do this or this. We could do these two things. And they're like, really? 2 things? This is what you got? Anyhow, and the guy was really nice about it. And anyhow, later on, this guy came up to me and he's like, what would you make if I gave you some lemons? If I gave you some lemons, what would you make? I was like, I don't know, lemonade. He's like, yeah, that sounds good. He's like, what about lemon bars? What about that? What about a lemon cake? How about some lemon muffins? How about lemon schnapps? Go on and on and on. And so this is kind of like your lemon, right? What can you do with this? And the answer is many, many different things. And we said, wow, we could react it with a hydroxide. You see in the first one here, and we would end up with an alcohol. We said, okay, we could react it with an alkoxide, and we could make an ether. We could react it, this is called a bisulfide here. If we did that, we'd end up with a thiol. If we reacted it with acetate, okay, with acetate, we end up with an ester. You're like, oh man, it's like IR is rearing its ugly head, all these functional groups that we talked about in infrared spectroscopy. If we react with a cyanide, okay, so if we react with a cyanide, then we get what's called a nitrile. So remember, a nitrile, C triple bond N. And then if we react it with something like, this is called potassium tert butoxide. So potassium tert butoxide. Okay, potassium tert butoxide, you end up with an alkene. Okay, so end up with an alkene. Now again, there's a lot of information on this slide, but you and I want to know how to make a lot of different compounds. And so already we've figured out we can take an alkyl halide and we can do many different things with it, okay? And if you're wondering, do I have to know all these things? The answer is yes. And we're going to take a look at it throughout the chapter, and you're going to practice it. You're going to start to sort out in your brain. You're going to say, okay, this is going to make this, and so on and so forth, right? Let's do a real deep dive on this whole idea of the SN2 mechanism. Again, I told you we're going to study SN2, E2, SN1, and E1. I'll just tell you, since I figure I have your attention for the first few minutes of class, I figure everybody's still paying attention right now. The SN2 and the E2 are used more often than SN1 and E1 reactions, and that will become clear when we take a look at SN1 and E1 reactions. However, you can imagine you're in the class, okay, and I'm teaching the class, right? SN1 is still very important for us when we're learning the material, but again, SN2 is more widely used. Let's take a look. The SN2 mechanism. Remember last class, we said the S stands for what? Substitution, right? The N stands for nucleophilic. And what did I tell you this 2 stood for? Does anybody remember? Okay, do you guys remember, and I know you do remember this, who remembers, I know a few of you people sitting right here, some of you were in my Gen Chem 2 class last semester. Wasn't it an evening class that we had? Yeah? Remember the first chapter we did was kinetics? Rate is equal to K times the concentration of something times concentration of something. And at first I gave you all these ungodly orders. I'd say 5th order, figure out what the units of K are, and I was just testing you to see if you could figure out the units of K. But then when it came down to integrated rate laws, do you remember we only studied 3? We studied a zero order integrated rate law, first and second. Okay, so the 2 is a second order reaction and the 1 is a first order reaction. 0 order reactions aren't going to play a role in this class whatsoever, okay? Now again, I think you guys have very good memory, so I'm going to kind of skip ahead in the content a little bit here. You guys remember this. If you have A gives you a product, and again, this is from Gen Chem 2, whether you took it here or anywhere else, okay? You would say rate is equal to K times concentration of A to the power of X. Give me a thumbs up if you're like, oh man, it's all coming back to me now. Yeah, it's not flooding back, okay? Well, what it's saying is this. It's saying the rate of this reaction, okay, rate would be equal to K times the concentration of your alkyl halide, which in this case is this, times the concentration of your nucleophile. That's what the rate law would be. Thus, listen to me very carefully. The rate of the reaction depends on the concentration of 2 things, doesn't it? Right? It depends on the concentration of your substrate, your alkyl halide, and it depends on the concentration of your of your nucleophile in this case. Now, let's go back to our Gen Chem 2 even further, okay? If let's imagine K was 1, right? Imagine K is just the number 1, okay? Well, let's imagine the concentration of the alkyl halide and the nucleophile are both 1 mole per liter. 1 times 1 times 1 gives you what? 1. So you'd have a rate of 1 mole per liter per second, right? What would happen to the rate? I'll ask you guys. I'll put it on my pencil. What happens to the rate of the reaction if we doubled the concentration of the nucleophile? What would happen to the rate? It would double, right? You'd have rate is equal to 1 times 1 times 2. You with me on that? What would happen if you tripled the concentration of the alkyl halide and just leave the nucleophile the way it is? It would triple, okay? Now I'm really going to blow your mind. What would happen if you tripled the concentration of the alkyl halide and you doubled the concentration of the nucleophile? What would happen then? 6 times, right? That's it. That's it. That's all there is to a second order reaction, right? It depends on the concentration of both, okay? So going back to this idea of a stepwise mechanism, you noticed, or you probably noticed here, and I didn't write it down, but this alkyl halide is a primary alkyl halide, right? When we have our SN2 reaction, our nucleophilic attack, and our loss of leaving group happening simultaneously. Again, if you want to write it down, SN together, right? However, and we're not going to look at this probably today because it's section 7.9. I doubt we'll get there. We'll maybe do it Friday. When you have the stepwise mechanism, and I'll just blow the lid off of this. This is an SN1 reaction, right? It's SN1 at a time. First you get a loss of leaving group, and then you get a nucleophilic attack. Now, if you're sitting there going, well, why would both happen at the same time, and the other one, just a leaving group leaves first? Let me ask you this. When this leaving group leaves, do you guys remember what kind of carbocation this is? I asked you a question about carbocations on the last. What kind of carbocation is this one? It's a tertiary carbocation, right? Because the carbocation is attached to 3 carbons, okay? So this is a tertiary carbocation. Now, don't write this down, okay? Do not scribble this down because I'm going to rebuke it, okay? But let's just say, and again, I could be, this is America. I could get in serious trouble for doing this kind of stuff, okay? So if this leaving group and I said, do not write this down, okay? I'll call your parents if you write it down, okay? Mr. Dion's breaking the law here, okay? Would that ever happen? What kind of carbocation is that? Primary. Which one did we say was more stable, a tertiary or a primary? A tertiary, right? If you remember, last chapter, do you remember I drew a primary carbocation and I literally put an X over it? Remember I said this is so unstable? This is why this can't happen, right? Again, I know we cover a lot of information in this class. I'd be the first guy to admit it. However, there's a logic to basically everything we do. As long as you know the rules, you can usually kind of suss out, like, why would this happen? Why would this not happen? The reason SN2 reactions happen is because a primary alkyl halide cannot lose a leaving group, right? Without a nucleophilic attack happening simultaneously. Whereas a tertiary alkyl halide is like, whatevs, I don't care. I don't care if I lose a leaving group. I'm tertiary, right? It's like, I'm stable, right? Whereas a primary is like, this shouldn't be happening right now, right? Anyhow, there you go. Going back to the mechanism, we already uncovered this as a group. We said the S stands for substitution. We said the N stands for nucleophilic. And we said the 2 stands for second order. We said the way we would write a rate law for this reaction, I don't have it written here, but I can write it again. So for this reaction that you see here on the page would be rate is equal to K times concentration of whatever this is, our CH2X, okay, multiplied by concentration of your nucleophile, for this particular example that I have on there. Does that make sense to everybody, right? And they're superscripts in case, if you're like, is the superscript 1? Yes, but we leave that out, right? Cool. Here you go. So rate laws are back, okay? So we have a second order reaction, SN together, and we have the first order reaction, which is SN one at a time. Okay, you guys ready for a lightning round? Here we go, because I already asked you this question like 3 minutes ago. It says the following substitution reaction exhibits second order kinetics and is therefore an SN2 reaction. What would the rate law look like? Rate is going to be equal to K times the concentration of our substrate, which is our alkyl halide, which is just this, times the concentration of, is the sodium playing a role here whatsoever, right? What kind of ion is sodium? Spectator. So you can just leave it out. If you're dying to put it in, Don't, okay? We leave it out, okay? We just leave it out in organic chemistry. So we'll put here hydroxide. All right, so let's answer these very quickly. In A, it asks, what happens to the rate if the concentration of iodopropane is tripled and the concentration of sodium hydroxide remains the same? Well, if the rate was equal to, let's say, 1 times 1 times 1. I'm just throwing in any old number in here. And then we triple the concentration of the iodopropane, it would be rate is equal to 1 for my K times 3 times 1, which is going to give me 3, right? So it's going to be 3 times faster. In the second one, it says, what happens to the rate if the concentration of one iodopropane remains the same and the concentration of the sodium hydroxide is double? It would mean rate is equal to K, 1 times the concentration of our substrate, which is 1, times the concentration of the hydroxide, which is 2. How many times faster will it be this time? Everybody?
2.
In unison. We'll do it like, at 2, right? I want everybody to say it, okay? 2 times faster. I'll let you guys just yell at me. What's the answer to the last one? You're doubling the concentration of the 1 iodopropane and you're tripling the sodium hydroxide. What would it be? There you go. Thank you. Like I said, don't be afraid to holler out in my class. All right, so rate is equal to 1 times 3 times 2. I don't have a calculator, but yeah, I think you guys are right. 6 times faster. There you go, my friends. That's it, okay, for your rate law. And if you're like, where did you get those numbers, the ones? I don't know. I pulled them out of thin air. I just made them up, okay? I figure I can do 1 times 1. This is something I can do, okay? So I just put in 1 as a concentration. You can put in whatever number you want and then double your concentration or triple your concentration and then just compare the two rates. You're going to get the same answer no matter what you do. Okie doke. Let's keep going. How does the observed stereochemistry in the reaction support an SN2 mechanism? Well, I don't provide too much information about this, but remember, I expect you to read the textbook in this class, but you notice you're starting out with an R compound, and after the SN2 reaction occurs, you end up with an S compound. There's a name for this. When you flip your configuration, we call this inversion of configuration. Sometimes people describe it as like an umbrella flipping in the wind. Has anybody ever seen this? Or maybe you've been a victim of it. You know, you're walking around with your umbrella and poof, right? It flips the other way, okay? On a really windy day or something like that. Now, why does this happen? There's actually 2 reasons why this happens. One is, let's just think about this in terms of electronics. If we look at the electrophilic carbon, or alpha carbon, right? We know this is delta plus, and we know the bromine is delta minus, right? Is that nucleophile, right, that bisulfide, which is negative, is that going to want to come near that bromine that already has a partial negative charge, right? We know that like charges repel each other. And so what happens, and this is not a joke, okay, the nucleophile attacks from the back side like this. This is your nucleophilic attack. And then we have our loss of leaving group occurring. And we actually have a name for this. We call it backside attack. So backside attack. And when we have backside attack on a stereocenter, it results in inversion of configuration. Now, you guys can bear with me for just a second. If I switch over to the textbook, I just want to show you a figure that's in here, okay, very quickly. You see this figure here? Okay, it's figure 7.2, and it shows you front side attack does not occur, right? You could even say sterics, right? A bromine is pretty big, okay? You could say it's an electronic effect, okay? And thus, the nucleophile comes from the back side. And when it does, it flips those 3 groups. The methyl, the ethyl, and the proton, they get reversed, okay? So we call that backside attack, or backside attack on a stereocenter results in inversion of configuration. Thus, if you're starting with R, it becomes S. If you're starting with S, it would become R. Cool? Does that make sense to everybody? So backside attack. Now, the textbook, this is the explanation that I gave you. Electron density from the bromine repels the attacking nucleophile. The textbook goes into a whole explanation using highest occupied molecular orbital and lowest unoccupied molecular orbital theory. However, I'm just going to skip over that and say I will not ask you anything about that, okay? I would say that would be more of a chemistry majors thing, so I'm not going to stress about that. However, I would stress about a question like this. Maybe not stress, I would maybe enjoy it. But it says here, draw the product of the following SN2 reaction. Could you guys draw the structure of S2-chloropentane? I'll give you a second to try and draw that. S2-chloropentane. My brain and be like, which one is S and which one is R? Oh, yeah. What I do is this. Okay, you ready? Here's Mr. Dion's express way of doing this. Is I'll just say, okay, 2-chloropentane. 1, 2, 3, 4, 5. I always start with a dash first. And if it's wrong, I should color it in. And then I'm good, all right? So that's what I do. So I'll just say, I'll just try this and see where it takes me, right? And then I'll say, well, this is 1, this is 2, this is 3. So it looks like it's clockwise, which would be R, but we know it's reversed because the proton is coming out towards us. And so this is the right compound. If it had been wrong, all I do is take that dash and I just scribble it in with my pencil and I'm done, okay? So there we go. S2-chloropentane, and we're going to react it with sodium bisulfide, so Na plus. I'm going to draw in all my electrons, right? Remember organic chemistry, focus on the electrons, right? So if this is an SN2 reaction, we have to draw the nucleophilic attack and the loss of leaving group occurring simultaneously, right? What's it going to look like? Here's our nucleophile. We're going to draw a nucleophilic attack on our alpha carbon, right? That's our electrophilic carbon. We went over this in chapter 6. Which carbon is electrophilic? It's the one attached to the chlorine. Is chlorine a good leaving group? Acha. Yeah, it's a beautiful leaving group. So that's going to happen. Now when we draw our product, which is going to be a thiol, the sulfur analog of a thiol, the sulfur analog of an alcohol, am I going to draw, Heidi, can I ask you? I just saw you were doing. Am I going to draw a dash or a wedge, Heidi? What should it be? A wedge, right? Because I get what? Inversion of configuration. Exactly. There we go. So let's scribble this down. Wonderful. There we go. So, and you can check yourself. You can say, okay, well, this was an S compound. Is this an R compound? You look at it and you say, yeah, that is definitely an R compound. And thus, we had inversion of configuration. Come on. Configuration, and we had backside attack. Backside attack. Now, if you're wondering, since it's backside attack, is there a special place I'm supposed to put my arrow for my nucleophilic attack? No. You can draw it any way you want. The way you're actually representing that you understand that it's backside attack is by taking that dash and flipping it to a wedge. Okay, I don't give a darn where the arrow is. Meaning, let's imagine, I don't know, somebody in the class said, I drew my curved arrow here. It's the same thing, okay? It's the exact same thing. But when you take that dash and you change it into a wedge, you're telling me, yes, I understand. This is an SN2 reaction. I get backside attack and I get inversion of configuration when I have an SN2 reaction. Cool? There you go. All right. Now, one thing I love about teaching science students is that they're all very good at drawing conclusions, right? You guys are probably sorting this out in your brain as I'm speaking, and you're saying, well, if a nucleophilic attack and the loss of leaving group are going to occur at the same time, that would mean the less stuff, you shouldn't use the word stuff or thing if you're a scientist, but just allow me for a second here. If you have the less stuff you have around your alpha carbon, the easier the nucleophilic attack can occur, and you would be absolutely right. Thus, when it comes to reactivity towards an SN2, and again, these are things, you're going to look at a molecule and you're going to say, that's a primary alkyl halide. That would be prone to an SN2 reaction, right? My nucleophile can just attack. There's nothing in the way. Wow, I've got a methyl halide. There's nothing in the way of that carbon. It's just 3 little protons. Are you with me on that? So methyl halides are going to be the most reactive. Then we go up to primary. Secondary, not so much. And tertiary are virtually unreactive. You would say, if somebody says, if you're sitting in the science center and somebody says, here's a tertiary alkyl halide, let's do an SN2, you say, no, it's not. Okay, it's not going to happen. Okay, just forget about that. That doesn't occur. All right, and I'll show you a little bit of reaction rates. So check this out. Now, I'll sort this out for you. All this is showing is a nucleophilic attack by an iodide ion on some kind of alkyl bromide, okay, in acetone. Acetone is nail polish remover. It's an organic solvent at room temperature, so this is just a regular old SN2. That's all you need to know, is you just say, yep, these are all SN2 reactions. Well, look at this. And don't worry about this side yet, we'll come back to it. If we look at just the effect of alpha substituents, if I compare a methyl alkyl halide, it's a methyl bromide, to a primary, to a secondary, to a tertiary, if they assign a value of 1 for the rate of the primary alkyl halide, look at the methyl alkyl halide. It happens 145 times faster. That's a lot faster, right? Then you go down to the tertiary and it just says, forget about it. Don't waste my time, okay? It doesn't happen, okay? Then if you're like, man, organic chemistry is neat, you know, I can already start to draw some conclusions very quickly. So sometimes students will say, okay, primary alkyl halide, always reactive in organic chemistry. Well, not so fast, okay? What about substituents at the beta carbon? So if we go 1 carbon away, you notice that each one of the examples here, you notice every single one of these is primary. Look, this alpha carbon is attached to 1. This one is attached to 1. This one is attached to 1. Right? Every single one of these is a primary alkyl halide. But you're saying, hey, there's also an effect on beta substituents. If I go from just the one beta having just hydrogens attached to it to having a carbon, basically doesn't affect it. Even if I have 2, it still works, right? This reaction works. But then if I go down to 3 substituents on my beta carbon, it's virtually unreactive. And this is a trend. It's a very specific trend, but it's shown in, I would say, all organic chemistry textbooks that I've taught from. And I read the textbook, believe me, I read your textbook. And I don't know if he said it or not, but there was one place in the textbook where he said, this example here is a good reason why you can't memorize your way through everything in organic chemistry. You can for some stuff, sure, you can memorize pKa's and be the boss, you know. However, right, with something like this, you can't just say, yep, it's a primary alkyl halide, it's always reactive. You're like, well, turns out no, right? If I have 3 substituents there on that beta carbon, it's not so reactive, right? Now, if you're wondering, are you going to keep throwing this thing at me over and over and over? No, I probably won't even ask it on a quiz unless it was a bonus or something like that. But it's just a pretty cool thing to think about. Anyhow, you know, like I always say, every time I show a graph in class, what do I always say? There's somebody in class that needs a graph for everything we do. That's totally fine. So if we just compare reaction coordinate diagrams, this is just an SN2. You notice with an SN2, there's no intermediates, right? There's just a transition state at the top where the bond, in this case, between the carbon and the bromine is breaking, and the carbon and the carbon of the cyanide is forming the nitrile. If you're wondering about this whole thing here, this we call, no joke, this would be a good name for a bar. It's the double dagger. Okay, so you get the double dagger here, maybe a pirate theme, something, I don't know. Anyhow, so you've got the double dagger here. That's the symbol that we use that represents a transition state. It's just a symbol. I'm not sure where it came from or whatever, but that's the symbol all chemists use for a transition state. Remember what I told you in a previous chapter? Do you remember I said to you guys one day, I said, I will never make you draw a transition state, right, in a quiz. I said I won't bug you with that. But I said you should still try the practice problems where it says try to sketch a transition state, because I want you to understand, you know, bonds being broken, bonds being formed, that kind of thing. However, let's get down to the important part, which is this here. This is, if you can't see, I'll write it down. This is a methyl halide, this is a primary alkyl halide, and this is a secondary alkyl halide. These are all SN2 reactions, right? What do you notice with them? What increases as you go from methyl to primary to secondary? The what? The activation energy, right? Does activation energy affect rate? Yes, absolutely, right? The higher the activation energy, the slower the reaction. End of story. You're like, they left out tertiary. No, they didn't. They put it down here. Tertiary substrates, there's not enough room on the screen to put how high the activation, right? We would go up to the stratosphere or something, right? An extremely high activation energy. Cool? Is this making sense? Give me a thumbs up if you're even with me like 50% of the way this morning. Cool. Any questions about anything that's nagging at you? I don't want you to have a real question like bugging you in class or something. Okay. Well, let's rock and roll here. Now this neopentyl bromide, And you're like, what's neopentyl bromide? Neopentyl bromide is the compound I showed you a second ago, which is this guy here, okay, where your alpha carbon is attached to only one carbon. Technically, it's a primary alkyl halide, right? This is your beta carbon here. But we said even though neopentyl bromide is a primary alkyl halide, it reacts slowly. Why? Because it has so many substituents on the beta carbon. So this molecule, in case you didn't pick up on it, it's this guy right here. It's that very specific example, okay? As far as the MCAT stuff, I don't know if they test on that or not. I don't remember seeing it anytime recently, but I'm not studying for the MCAT. I look at review materials when a student wants me to or something. So you'll have to take that. That's what I can tell you right now. All right. So we discussed, did we just talk about alkyl halides for 40 minutes? Kinda, yeah, okay. What else do you need for an SN2? You're like, well, you got to set the mood. You need the right lighting. You need some music on in the background, right? You know, you got to get in the organic chemistry mindset. Maybe have your book open or something like that. So we've decided we need an alkyl halide, but we also need what? Starts with N, ends with nucleophile. Anybody? A nucleophile. All right, so let's turn our attention. Let's shift our attention. We've gone through the alkyl halides. We said methyl was the best. Primary was good. Secondary, middle of the road. Tertiary, not going to happen. Now let's talk about nucleophiles. You guys remember the difference between the strong and the weak of the nucleophiles? What kind of charge did a strong nucleophile have? Negative charge, right? What kind of charge did a weak nucleophile have? No charge, right? I said water was a crappy nucleophile. I said it's a nucleophile, but it's not a good one. It's weak, okay? I said an alcohol, right? Again, you guys and me, we train our eyes as organic chemists, and we look at these reactions and we say, oh man, look at that. Methyl iodide. Oh, that's a crazy reactive in an SN2. Then in this one on the top, you'd say, oh yeah, strong nucleophile, super good alkyl halide or strong electrophile. SN2 is going to happen super quickly. And then somebody's like, oh, water? Are you kidding me? Water's not a good nucleophile. That's a terrible nucleophile. And again, you guys have to be able to say, well, one of these reactions is going to happen really quickly. It's going to be a good reaction. We'll make an alcohol. This is methanol. Right, whereas the other one, you just look at that like, that's no good. I can't do anything with this, right? Give me something I can work with here. All right, so you need to be able to recognize a nucleophile as being strong or weak. Generally speaking, if it's strong, it's got a negative charge. And if it's weak, generally speaking, it's going to be neutral. I'll add in here water and ROH, which represents an alcohol, okay? So you guys going to remember that? If it's got a negative charge, it's going to be a good nucleophile. Generally speaking, not all nucleophiles are created equal. Some are better than others, for sure. But generally speaking, that's a conclusion we can draw. Now, things that I would print out if I was a student in this class, maybe you print out the slides and you have everything. That's awesome. Maybe you don't like to print things out. That's cool too. But I would recommend printing this part out. You know, and how often do I say that? Almost never. I recommend printing this table out, okay, and putting it somewhere in your life so that you can look at this and say, yep, those are my strong nucleophiles. Let's see, I got the iodide, the bromide, the chloride. Those have negative charges. I've got the bisulfide, which is the SH ion. I've got RS minus. This is called a thiolate. I'll scribble it down here. This is called a thiolate. Right? If you've got thiol, which is RSH, if you remove a proton and have a negative charge in chemistry, 8. Thiolate. Then you've got a hydroxide. This one here is called an alkoxide. We're going to look at many alkoxides in this chapter. And then what's this guy called? No, it's a nitrile when it's attached to a carbon, but this anion is called, starts with C, cyanide. Right? This is cyanide. So cyanide makes a nitrile after a substitution reaction. Okay, let's make sure we know our ions. Then, boy, I feel sorry for these two over here. They're just all alone, you know, just the two of them like clink. I guess it's just me and you, you know, the weak nucleophiles are over there. No charge for us, all right? Anyhow, but don't worry, they have their place too. Now, do you remember my yarn that I gave you about something being polarizable? I said a golf ball is squishy to some degree, right? Then you got a tennis ball, which is bigger and squishier. Then you have a party balloon, which is big. Then I said you got a squishmallow, which is huge, but is more squishy than all of them, right? And so the more polarizable an ion is, meaning the bigger its electron, I shouldn't say the bigger, the more easily distorted its electron cloud is, the better nucleophile it is. And then as far as solvent effects on nucleophilicity, this is something I will address briefly at the end of this chapter. I'll go over it with you. However, we don't go into that much depth on solvents in this class. If you're a chemistry majors class, we go into solvents in dirty detail in there. But at the very end of this chapter, I'll show you a couple things about solvents, because I don't want you to come out of this class and say he never even mentioned what the solvents were. You should know a few solvents. Let's take a look at each of these, and this is where it starts to get, I don't want to offend you, but I'll say fun, okay? I'm going to use the F word and say I think this is kind of fun. It's where you start to put everything you learned this morning into practice, and you guys start to make some judgment calls, okay? I want you to look at these two reactions and compare them. I want you to look at these two reactions, and I want you to look at these two reactions. We're talking about SN2s right now. I want you to figure out which one of these two would be faster, right? And then why. So I'll give you a second to try and answer that. Right? We got two alkyl bromides. You have SH minus. Is that a good nucleophile? Sure, it's the same nucleophile for both. Same leaving group in both. What's the difference between the two? The first substrate, the substrate on the top, is what kind of alkyl halide is it? It's a secondary alkyl halide, right? What kind is the kind below it? Tertiary, okay? So we've got secondary alkyl halide here, and here we've got a tertiary alkyl halide. Everything else is the same. And we'll put here faster since secondary alkyl halide. All right, what about the second one, the one that I have the yellow line by? What's the only difference between these is the two nucleophiles. Which one's going to react faster, the one with water as a nucleophile or the one with sodium hydroxide? There you go. We'll say here, faster since OH minus is strong nucleophile. You can put here H2O is crappy, is a weak nucleophile. Now the last one, the cyanide, is the nucleophile in both. They're both secondary alkyl halides. What's different between the two? It's the type of what? The leaving group. Which one of these is a good leaving group, iodide or fluoride? Iodide is a good leaving group, right? We said fluoride wasn't a good leaving group. Let's scribble it down. We'll say here, faster since iodide is good a leaving group. And if you want to write down fluoride as a poor leaving group or as not a leaving group, as far as we're concerned so far, that's totally fine too. Isn't that neat? How you put everything you learn together, you say, hey, I can look at it from the point of view of the nucleophile or my substrate or my leaving group, right? And I can kind of suss it out and say, yeah, this reaction looks good. This reaction looks not so great. All right. Well, let's move on to the E2 mechanism. And in the SN2 mechanism, I would say I focused mostly on alpha carbons. When it comes to the E2 mechanism, we're going to look at alpha carbons a lot, and we're going to look at a lot of beta carbons. Okay, so remember, the beta carbon is the next door neighbor of an alpha carbon. Okay, you guys know what a strong base is. You know, if you have hydroxide, is that a strong base? Oh yeah, big time. Another strong base we're going to see a lot will be those alkoxides where it's OR minus, where the R could be a methyl group. That would make methoxide. If it's an ethyl, it would be ethoxide. If it's an isopropyl, it would be isopropoxide, etc., etc. When an alkyl halide is treated with a strong base, it can undergo what we call a beta elimination or a 1,2 elimination. They both mean the same thing. They're both an E2 reaction, which forms an alkene. Now you see I have the mechanism drawn here at the bottom, but you can practice it over and over. You can say, okay, what happens? I've got my alpha carbon. Okay, what I do is I go to a next door neighbor. And they're just using this one for instructional purposes here. They said beta carbon, and they drew a hydrogen, or there is a hydrogen, excuse me, on this beta carbon. And so what's going to happen is that the base is going to pick up the proton. Then the pair of electrons that's between that beta carbon hydrogen and the beta carbon is going to form the double bond, and then I get a loss of leaving group. So it's a collection of 3 arrows. We end up with our conjugate acid of our base, our leaving group, which has been lost, and we form a pi bond. And again, if you weren't here last class, which I think you all were, but if you weren't here at last class, I said, what's so great about this reaction is you make an alkene. If you looked ahead in the schedule, what's chapter 8 all about? The chemistry of what? Alkenes, right? Nothing but alkene this and alkene that. What's step 1? Know where to get yourself an alkene, right? At least now you know where to get one, right? You say, I'll make it my own self, okay? There you go. All right, so we call that an E2 reaction. What does the E stand for? Elimination, right? We're eliminating a hydrogen and we're eliminating a halogen. So what did we eliminate overall? In this case, we eliminated the H and the X. Okay, that was what is eliminated. Of course, they make a salt here in this case. They make the conjugate acid of the base plus this halide here. And what does the 2 stand for? Second order. It's a second order reaction. So if you were to write a rate law out for this, it would say rate is equal to K times the concentration of your substrate, your alkyl halide, times the concentration of the base. You're like, that's the same thing that it was for the SN2. That's right. Same thing. Depends on the concentration of 2 species. Okie doke. There it is. If you have, you're like, this is the same thing. All you do is replace nucleophile with base. Yep, it is. That's it. Okay. One's a substitution. One's an elimination. When does substitution occur? When you have a methyl alkyl halide or a primary. When does elimination occur? When you have a tertiary, in case you haven't noticed, right? I'm sure you've picked up on that already. So how are they similar? They're both second order. How are they different? Well, one's an elimination and one's a substitution, right? That's the difference between these two. All right. I'm going to shift gears for just a second and show you something that I think probably every single one of you has figured this out already in the class without even thinking about it really. You're like, usually when I present this, students are like, yeah, I kind of figured, you know. Remember, Heidi asked, we were talking about cis and trans earlier on. If we look at these 2 alkenes, you guys can tell which one is a trans compound and which one is a cis compound, right? Even if I hadn't, so this is called a space-filling model, where it tries to show the relative size of the atoms, right? You see carbon is bigger than a hydrogen. I won't ask you to answer this, but my guess is if I hadn't even put those space-filling models and put the words steric strain on the screen, I would bet money that if I'd asked you, which one of those do you think is more stable? You probably would have said the trans, right? You would have said, yeah, the 2 methyl groups are farther away from each other, whereas if I make the cis, then they're closer to each other, right? It's kind of like they're eclipsing each other in a way, right? And I would say you're 100% correct. So generally speaking, cis isomers are going to be less stable than a trans isomer. There are some exceptions to that, but generally speaking, that's a rule we can abide by. Furthermore, and if you're wondering, like, what are you doing? You were just talking about elimination. Now it's a lesson on alkenes. Like, what is going on? Well, what do you make when you do an elimination reaction? An alkene. That's why there's a little mini lesson here about alkenes. So number 1, trans alkenes, generally speaking, are going to be more stable than a cis. Second thing is you need to know the trend of alkene stability. And alkene stability, in my mind, my tiny little brain, it follows a similar trajectory as carbocation stability. The more substituents you have on the carbons in the double bond, the more stable it is, okay? Right? I get by with a little help from my friends. Thus, if you look at the 2 carbons of a double bond, right? There's 2 here, there's 2 here, there's 2 here, there's 2 here. You notice in the first one, there's only 1 carbon. I'll use a different color. We'll use black, okay? There's only 1 carbon attached to those 2 overall. The rest are all hydrogens, right? Whereas in the di-substituted, there's 2 carbons attached to it. You see where I'm going with this, right? In the tri-substituted, there's 1, 2, 3. And then in the tetra, obviously, there's 1, 2, 3, 4. We don't go into any explanation as to why. All we say is that the more substituents you have on the carbons in the double bond, the more stable it is. Okay, you going to remember that? Okay, well then let me ask you a question. Okay, so we got these 3 alkenes. They're all isomers of each other. I'll call this one A, I'll call this one B, and I'll call this one C. Based off of the rules that we saw in the previous slide, And again, don't be shy to holler out an answer in my class. If you get it wrong, it's not a big deal. Brianna, which one's the most stable? Yeah, absolutely, right? It's tetrasubstituted. The 2 carbons in that double bond are attached to 4 different carbons. Look, you don't believe me? Right? This is what she's saying. She said, look, there's 1, 2, 3, 4. This is the only one that's tetrasubstituted, and so this is the most stable. Brianna, could you finish it off here? Which one's the least? Yeah, B is the least stable, right? If we take a look at it, look, here it's got 2 hydrogens. Those aren't substituents, right? Those don't count, but it's got 2 carbons, right? So this is the least stable. Least stable. And then here you're somewhere in the middle ground, right? You've got a tri-substituted, and so it's somewhere in between the tetra and the di-substituted. Cool? So can we remember that? I hope so, because we're going to make a heck of a lot of double bonds coming up, okay? And we're going to look at different isomers that we could make, some that are more substituted, some that are less substituted. And yeah. What time is it? It's 8:58. We have an hour left. Like, what do you guys think so far? So far, so good? Nobody's run out of the room and been like, I'm out of here, not yet. So it seems like it's going pretty good to me. Okay. Let me show you this compound here. Okay, we've got this, what would you call this? 2-bromo-2-methylbutane is the name of this compound. I think we can all agree on that. Would you guys agree with me? This is an alpha carbon, yes? Now, could I ask you guys, obviously it's got some beta carbons here. How many different types of beta carbons are there attached to that alpha carbon? Not how many different beta carbons are there, but how many types? There's 2, right? There's 2 that are methyl groups, yes? So those are identical. And then there's another one that's on an ethyl group, so that would be different. So I'll use color coding here. I'll put beta, sorry. And then I'll put a beta here. Okay, so our conclusion is that we've got 2 different types of beta protons as well, right? So now what I'm going to do is, just for instructional purposes only, I'm going to draw 1 in here, okay? And I didn't really give myself a lot of space here. Oops, come on, you son of a gun. I'm not going to swear. So I'll put this here. Okay, so we'll put a beta here. Okay, so we've got these 2 different types of beta protons. Obviously, there's more than this, right? There's other green ones that I'm just not putting them in. Now, if I was to do an E2 reaction and abstract that green proton, and again, I could have put it there, or I could have put it here. It doesn't matter. Okay, either one. They're both identical. Okay, phew, thank God. All right, anyhow, so if I had pulled off that green proton, are you with me? That we would have formed a double bond between the green beta carbon and the alpha carbon, yes? Right? If you want to practice drawing the mechanism, you could, okay? You have your ethoxide, which is negatively charged, right? You'd pull off this proton, make the double bond, and lose the bromide like that, yes? Okay? What if I had pulled off the blue proton? If I pulled off the blue proton, I pull this proton off, I make a double bond, I lose my leaving group, and in that case, I would get this compound, okay? One you can see is named after somebody named Zaitsev. The other one is named after somebody called Hoffman. Can I ask you guys, between the Zaitsev and the Hoffman, which one of these is more stable? The Zaitsev, right? It's a tri-substituted alkene, whereas the Hoffman is a di-substituted. So we'll put here, Zaitsev is more substituted, therefore more stable. And if you want to write next to the Hoffman, it's less substituted, ergo less stable. That's totally fine. Okay, let's see what it says here. When ethoxide, OET minus, is used as a strong base, 2-methyl-2-bromobutane gives you 2 products that are shown here. The more stable product, the Zaitsev product, is the major product, and the less substituted alkene is the Hoffman product, the minor product. The thing is that an ethoxide is actually a pretty small base. If you think about it, ethoxide has an oxygen with a negative charge, and then it has CH2CH3. It's not very big, that alkyl group, right? What you're going to see in a few seconds is that if we replace that R group with a big old giant tert butyl group, right? Would you agree with me that this tert-butyl group is much, much bigger than that ethyl group? Since a tert-butyl group is so big, it's actually going to have difficulty pulling off that blue proton, right? Because that blue proton is on a carbon that's attached to 2 carbons, yes? Whereas the beta carbon in green is only attached to 1 carbon. So that green proton is less sterically hindered. And so it's kind of like the tert-butoxide, or the tert-butoxide ion can come in like a surgeon, right? But it can only pull the ones that are easier to grab. Does that make sense? Even though at the cost of stability. It makes something that's less stable. So let's take a look at that. Again, we say that since the ethoxide forms the Zaitsev product in a greater amount, as a major product, we say it's regioselective. Think of that word. Everybody here knows what it means to be selective, right? You go to a buffet restaurant, you're like, I am selective for the ice cream over the Brussels sprouts, or something like that, right? It's selective. You might get a bit of both, right, Micah? But you take more of one than the other, right? So regioselective. It doesn't mean that it doesn't take some of those green protons that I had on the previous slide. It just means it's selective. It likes the blue ones more. Why? Because it makes a more stable product, right? So we say the reaction is regioselective. Now, if you're wondering, am I expected to know this? Yes, you will be expected to know, in this case, with ethoxide, that this would be your major product, and this would be your minor product. Now, here's where it gets really interesting. Like I said, with the tert-butoxide, we're going to see in a second that the Hofmann is going to predominate. This is what I think, and again, I realize that I like the subject, okay, and I realize that not everybody else does, but I'm teaching, so just bear with me, okay? This is what I like as an organic chemist. I like the feeling of saying, okay, I got this alkyl halide. I can go to the cupboard, take out a reagent, and decide or control which alkene I'm going to get, right? I choose ethoxide. I get the Zaitsev product. I go grab some tert-butoxide. You're going to see I'm going to get the Hofmann predominating, right? You're like, that's kind of neat. You can make whichever one you want, Yes, that's your answer. And so this is kind of a distribution being shown here, product distribution. If we have our ethoxide, this is what we've already seen. With ethoxide, you get mostly the Zaitsev product. But check this out. This is your tert-butoxide. This is that thing that I drew a few seconds ago. Look at this. Now you get the Hofmann product as the major product, right? Don't worry about this base. This is never going to come up in our class. He just put it here for illustrative purposes. He said if you use this hindered base that's even more hindered, right? It's got these 3 ethyl groups instead of methyl groups. An ethyl is bigger than a methyl. It even favors this even more. But again, the only 2 of these bases you will see will be the ethoxide and the tert-butoxide. Okay? So again, if you want to write these down, if you want to get the vernacular down, this is called an ethoxide. This is called a tert-butoxide. All right? Tert-butoxide, the Hofmann will predominate. An ethoxide or a methoxide, and you would say the Zaitsev product is going to predominate. Now, as far as other big, bulky bases, okay, organic chemists, they all love reagents, okay? They love reagents. They're like, give me a reagent, give me a new reagent. They're like, boy, am I ever excited. I did a job interview one time, and the guy was so polite and so I don't know if it's a backhanded or condescending or whatever, but I remember I did a job interview one time, and the guy was like, and this is after I had 2 degrees in organic chemistry. He's like, now, Dan, when it comes to reduction, you probably know maybe 6 ways to do a reduction. And I'm like, sure, I guess. And he's like, but I know all the ways to do reductions. I'm like, gotcha, buddy. All right. So whatever. He was probably telling the truth. He had a lot more experience than me. He'd been doing it for 30 years. But I remember thinking, like, this is strange. And it was kind of an interesting thing. But organic chemists, I'll just tell you, they love reagents. Okay? And you're like, why do they love reagents so much? Because science, right? Do organic chemists that do this for a living, do they sit around and work on molecules that people have made before? No, they're pushing the boundaries of science. They're making new molecules every day. They're unsure about reactivity sometimes. They have ideas. And so they try this base and they say, well, I get, mostly this. Then they'll say, I'll try this one too. Then I'm going to try this one too. Whichever one gives me the best yield, I'll move forward with that one. Does that make sense? Right? Sometimes it can be a cost thing. Sometimes it can be a percent yield thing. Sometimes it can be a safety thing, but chemists love different reagents. So if you're looking at, sometimes every once in a while a student raises their hand like, why do I need to know 4 ways to do the same thing? Couldn't I just have one way? Well, chemists like to know a bunch of different ways to do the same thing. Thus, some other sterically hindered bases that we like besides T-butoxide, you can see that we've got a couple of amines here. One is called triethylamine. We have an acronym for that, is TEA. Triethylamine, you guys can just call it triethylamine. You can just write the structure. It's an amine with 3 ethyl groups on it. Then you see here we have diisopropyl amine. And so there's probably an acronym for that too that escapes me right now. But again, you can see why these are, right? Amines are organic bases. Okay, if you don't know that, maybe I should write that down. Amines are organic bases. I think you know that. I mean, ammonia, right? Proton acceptor, right? Anyhow, amines are weak bases. So yeah, they're just bulky bases. Okay, let's move on. Now, let's see if we can put it all together into a big mechanistic product figuring out sandwich, okay? We've got, what kind of alkyl halide do we have here in the one on the top? Is this primary, secondary, or tertiary? Anybody? It's not a trick question. The first one with the chloride on it, it would be tertiary, great. We can scribble that down. Now, tertiary. What can I do with a tertiary alkyl halide? I don't know. Does a tertiary alkyl halide react in an SN2 reaction? No. Okay, that's off the table. What's my reagent? Ethoxide. Ethoxide is a strong nucleophile, sure, but I know this can't react in an SN2. Ethoxide is also a base. Could I do an E2 reaction? Yes. Now, is ethoxide a hindered base, like a big old bulky base, or is it a small unhindered base? Unhindered base, okay? Thus, if I look at my alpha carbon, would you guys agree there's 2 types of beta protons? There's these ones here, right? But then there's also, I'll use my black pen for this one here, okay? There's also this one here. Now remember, the ethoxide is like a ninja. It's very small. It can get into any place it wants. It's like I can go here, I can go there, right? Nobody's gonna stop me. If which proton would I pull off? The blue one or the black one is gonna give me the more stable alkene? Can anybody tell me? You guys wanna draw them? Let's draw the 2 products. So if we pulled off the blue proton, then I would form a double bond between this beta carbon and the alpha carbon. It would look like this. We would have these 2 methyls, which are unaffected, and I would have a double bond here. If I pulled off the black proton, I would end up with something that looks like this. Now, can you tell me which one of these is more stable? Would it be the blue product or the black product? Anybody? The black one, right? Because it's tri-substituted, right? Whereas the blue one is di-substituted, okay? So this is what we have to be able to train our eye to be able to do. And thus, I will write over here, I will say major product. If you want to put here, it's got a name, the Zaitsev product. And here we'll put minor. We'll call it the Hoffman. Wonderful. There we go. Good? Does that help? All right. Can I give you guys a second to try the next one? But before you do, let's just all agree. The next one, the only difference between the 2 of them is that one is using hydroxide and the other one is using tert-butoxide. Would you agree with me that there are 2 types of beta protons? There's this type of beta proton and there's this type of beta proton. Yes? Okay, I want you to see if you can draw the products of these, of both of these, and figure out, which one is the major, which one is the minor. You know what? Just draw the major one of each since we're kind of running low on time right now. If you're unsure, what you can say is the hydroxide is an unhindered base. It's very small, so it can pull off either one of these, the red or the blue proton. So you could just draw both products and say, well, whichever one is more stable, that would be my major product. If it pulled off the blue proton, oops, and I know I didn't even tell you to draw the minor product, but you would end up with this, okay? And if it pulled off the red proton, you'd end up with this. Which one of these is more stable, the blue product or the red product? The red. Therefore, this is going to be my major product, and this is the Zaitsev, okay? Remember, a T-butoxide, so this potassium T-butoxide, that's this. It's when you have a tert-butyl group attached to your oxygen, and the potassium is the cation. Is that an unhindered base? Just give me 1 second. It's severely hindered. This thing is huge, right? It's like so big, right? So it's got the option of either plucking this hydrogen off here on that beta carbon that is attached to one carbon, or it could grab this one here on this carbon that is attached to two carbons. It's going to preferentially pull off the blue proton and make the less stable product. Go ahead, Adam.
So is it a major product because it's a Zaitsev, or is it a Zaitsev because it's a major product?
No, the Zaitsev just means the more stable alkene, more substituted. The Hoffman means the less substituted, less stable. Whether it's major or minor, you have to look at the base.
Sorry, I meant stable instead of major.
Yeah, so the Hoffman and Zaitsev has to do with stability and substitution. Major and minor are going to be governed by the base that you choose. Does that help? Yep, there you go. So this is going to be our major, and this will be the Hoffman, okay? Hold on, don't leave, don't leave. We have just a second left, okay? I just want to